I am Antti Honkela from the Finnish Center for AI and the University of Helsinki, and I will be presenting our recent work led by Tejas Kulkarni and Jonas Jälkö on locally differentially private Bayesian inference. The setting we are considering has end users, each with their own data, depending on some common parameter of interest, theta. This common parameter, theta, can be something like the mean of the dataset, its variance, or frequencies of discrete items in the dataset, or regression coefficients of logistic or linear regression, in which case the data elements would contain both the input and the target variables for the regression. We are working under the LDP model, where each user applies a local randomizer into their data and then shares the result. We formulate our problem as a Bayesian model, where our goal is to estimate the posterior distribution of theta, given the noisy data shared by the different users Z. We can write this model as a joint distribution for x, z, and theta as a product of terms representing the local randomizer, the likelihood of the underlying model without DP, and the prior. So why would we apply Bayesian model in this Bayesian inference in this setting? Unlike previous approaches for LDP, with Bayesian inference, we get consistent inference on theta with no need for ad hoc corrections to make sure that the estimates satisfy some constraints, such as positivity or non-negativity. As a result, we get a posterior distribution of the possible values of theta, which provides us with error bars and allows evaluating statistical significance and making probabilistic statements such as which items are likely to be above or below a certain frequency threshold. Our work builds on a number of previous papers in the central model, starting with the seminal work of Williams and McSherry from 2010, continuing with a series of papers by Bernstein and Sheldon, and also building on our own recent work from ICML this year. Our methods are easy to implement using standard probabilistic programming tools, such as STAN. And from a DP perspective, they have the convenient property that all the inference we run is just post-processing, so it has no impact on the DP guarantees. Our methods are also fully compatible with shuffling for privacy amplification. The main challenge in applying Bayesian inference in this kind of model is that our model contains n nuisance variables xi corresponding to the unnoised original data for each user. We propose two solutions for eliminating these. First, using sufficient statistics, where instead of dealing with the individual variables, we are always dealing with the sum, which is applicable for suitable models, such as Gaussian model with Gaussian local randomizer, that can be applied, for instance, for linear regression and also with suitable approximations to logistic regression based on our ICML paper. If this is not possible, another possibility is to apply explicit modularization of xi, which is possible for certain class of models, mainly things like Gaussian and Laplace and randomized response mechanisms, together with suitable tasks. This explicit modularization also has the benefit that it can model clipping explicitly. Here is a concrete example of applying our work to synthetic data for histogram estimation using the optimal unary encoding by Wang et al. From the top curve, we see that our estimates provide a significant reduction in the RMSE of the frequencies of the data, especially in the difficult, tight privacy, low sample size regime. We also have a reduction in the number of cases where we are unable to correctly estimate the frequency ordering of the items. The second example here is with logistic regression on UCI adult, where we again see a significant improvement over LDP SGD, especially in the tight privacy regime. To conclude, We presented a method for consistent inference as post-processing to common LDP mechanisms. Our Bayesian approach provides error bars and measures of statistical significance. And in order to realize it in practice, we use sufficient statistics and marginalization to enable efficient inference. For more details, please see the preprint that is available on arXiv. Thanks.